have a three-dimensional point in the camera frame. So remember, we've gone from some arbitrary world frame to the three-dimensional frame of the camera, and we go from that to the homogeneous pixel representation, like that, in the image, and the matrix that takes them from the camera to the image, that's the intrinsic matrix. Okay, so that matrix represents the intrinsic parameters. All right? Now, fortunately, we can make it look even nicer than this. The first thing to notice is that the last column of K, when I write K as a 3 by 4, the last column of K is zeros, and that doesn't really do very much, so we can get rid of it. And then we can do even more. Here we have our kinder, gentler intrinsics. We can use a simpler notation. Like I said, we're going to remove that last column, and we've gotten rid of the explicit thetas and things, and you'll notice that we have the 5 degrees of freedom. We have F, which is focal length, A, which is aspect ratio, S, which is for skew, and CX and CY, those are the offsets. By the way, remember I said that we could have two different scales, right? A scale for one and for U and a scale for V? Or what we can have is a focal length and a relative scale between the two. Normally we tend to think of it that way, as a focal length, that's the overall focal length of the image, and then if there is a non-uniform relationship between the width and the height, we include that as an aspect ratio. And that's why there are 5 degrees of freedom. Okay? Now it turns out this can get even easier. All right? And the way it gets really easy is we assume a certain niceness of the universe. Okay? The niceness of the universe that we might assume is if we have square pixels, if there's no skew, and if the optical center is actually in the middle, okay, then we have no A, we have no S, we have no CX, we have no CY. All we have left is F. F is the only degree of freedom left. So when you're doing a calibration, sort of a lightweight calibration, what you'll do is you'll just search for F, assuming that your optic axis is in the middle, assuming there's no skew, and assuming that your pixels are square. Quiz. The intrinsics have the following: a focal length, a pixel X size, a pixel Y size, 2 degree offsets, and a skew. That's 6. But we've said there are only 5 degrees of freedom. What happened? A. Because F always multiplies the pixel sizes, those 3 numbers are really only 2 degrees of freedom. B. In modern cameras, the skew is always 0, so we don't worry about it anymore. C. In CCDs or CMOS cameras, the aspect ratio is carefully controlled to be exactly 1.0, so we don't model that anymore either. Well, the answer, as I said, is A, right? We have the F can be multiplied by A for the 2 different scales, or we can have the 2 different scales, but there aren't 3 numbers there, there's actually only 2, and so the answer is A. So now we found the intrinsic matrix, and last time we found the extrinsic matrix. So now we can combine them to get the total camera calibration that goes from a world point all the way through the camera coordinate to the image. So we write down our 2 equations here. We have our intrinsic P prime is equal to K times the point in the camera frame, and our extrinsic, which relates the world point to the camera point. P in W is the world 3-dimensional coordinates. Transformed by the extrinsic matrix becomes the camera 3-dimensional coordinates, which is used also in the intrinsic equation, and then that's converted to pixels directly. One thing to note here is that our world coordinate system is a 4-vector, it's a homogeneous, and we get out a 4-vector, but as we said before, for our K, instead of using the 3 by 4, we can use the 3 by 3, in which case we just use the XYZ of the point in the 3D camera space. We don't have to use the whole XYZ1. That's basically saying that this K can be thought of as a 3 by 4 or a 3 by 3, and when it's a 3 by 3, we don't have to have that 1 on the bottom there. So, putting these 2 equations together, what we have is we take a world point here, we pump it through our extrinsics, so this is a 3 by 4 matrix, okay, which gets us out a 3-dimensional vector, and then we pump that through our intrinsics matrix, and that gets us our homogeneous image coordinates. So this is a 3-vector. Remember we said it was Z times U, Z times V. Look at that, my U's and V's look the same. Divided and Z, and then we convert it back. And so this whole thing can be written as a single matrix M. M for calibration in some language. I have no idea why it's called M, but we call it M. Just want to write that M in a slightly different way because it's the way that we're actually going to make use of when we solve for this thing. So here we have the same equation written out. You see we have the world coordinates mapped through M gives us the homogeneous pixel coordinates. And what I've written here is I've taken this M matrix, which remember is a 3 by 4, and I said that you can think of it as 3 vectors, each of length 4, transposed as the rows. So each of these rows is a vector. I've also introduced something new here. I don't think I showed it on the slide before. Remember, this is what we said before. Okay, I'm using S as a scale instead of Z, right? And so we have S times U, S times V, and S. And later, to get out U and V, we just divide by S. And I've put this little operator here, but it's just a squiggle with a straight line underneath, sometimes 2 straight lines underneath. And it's what's known as projectively similar. So you'll notice that this vector and this vector are exactly the same except for a scale factor. Right? The vector on the left has been multiplied by S, gives you the vector on the right. And remember, in homogeneous coordinates, or using the projective, those 2 vectors are essentially the same because when I use their values, I divide out by the last component. So that's what's referred to as projectively similar. So that's also introduced here. So just finishing, the way I recover U and V is I divide the dot product, the dot of the vector of the point P in the world with the first row divided by that dot product with the third row. That's what's right here. And then to get the V value, I do the same thing, but now with the second row. All right? So basically what we have to find when we're going to do camera calibration is we have to find those M elements. So finally, we can talk about full camera parameters or camera and calibration matrix. The camera in its matrix, M, and sometimes it's called pi, and that's what I've written here, as we know, is described by several parameters. It's got a translation, T, of the optical center from the origin of the world. We've got a rotation, R, of the coordinate system. We've got a focal length and aspect, F and A, pixels or pixel size, SX, SY, a principal point, that's the offset, XC, YC, or CXCY, and skew. And in this slide, the blue parameters are called the extrinsics and the red are the intrinsics. And we can put the whole thing together. We want to find this as a sort of a single matrix. M is going to be built up of all of the effects of our parameters. And so that looks like this. Okay? What it says is that M is a combination of translate, this is extrinsic, and rotate. So now we have the point in the 3D camera coordinate system. Project, this is just the extraction of the XYZ, and then you pump that through the intrinsics. And how many degrees of freedom are there here? Well, there are 11. 5 for the intrinsics, 3 for the rotation, 3 for the translation. I'll get rid of all that scribble. That equation there, that M, that is the full camera calibration matrix. All right. That ends this lesson. What we've done so far is we've derived how the extrinsics and the intrinsics are combined to form a single calibration matrix. And this matrix maps from some arbitrary world coordinate all the way down to a pixel value. Some XYZ in the world, what UV does it end up in the image? All right? So what are we going to do in the next lesson? Well, the obvious thing in the next lesson is how would you go about finding that matrix? All right? And basically, the requirement's going to be, if I gave you the location of some 3D points in space, and I gave you the location of those points in the image, I should be able to recover that camera calibration matrix. And that's what we're going to do next time. And then a couple of times after that, we'll say, well, if we're less interested in going from a world coordinate system to a camera coordinate system, but instead we're interested in going from one camera coordinate system to another, remember that stereo thing? How would we do that calibration? But first, we go from the world to the image. All right, welcome back to Introduction to Computer Vision. Today, finally, we're going to get to talk about calibrating cameras, where we're going to be calibrating with respect to the 3D world. So, finally, we can get to the parameters themselves. If you remember last time, we solved for the full projection equation. that was made up of really a composition of the translation, rotation, projection, and intrinsics. For the rest of today, we're not going to worry about the fact that M has this internal structure till maybe the very end. We're going to think of M just this way. That is, M is going to be this matrix that's going to take your world points in homogeneous coordinates and eventually get you out your image points also in homogeneous coordinates. And what we're going to try to do is find that M. Fundamentally, at the heart of calibration is this idea of having some points whose three-dimensional location in the world we know, and that we identify them in an image. That is, we can find the correspondence between this point in the image is that point in the world, and then we have to compute some sort of a mapping from a scene to the image. And one thing you can do is you can actually put an object like this in the scene that has a bunch of points on it, and you've measured or you know something about the shape of that object, and you know where all the points are. Another way of doing it is to make use of, it's sort of the same math, but it's typically referred to as resectioning, which I'm pretty sure is a term that came from photogrammetry, which is a science that predates computer vision by about a century, that talked about going between images and three-dimensional world, typically used for mapping, cartography, and stuff like that. So in resectioning, which is what we're going to do here, the basic idea is we're going to have some known points. So on the right here, we have a picture of one of our labs, and one of the times one of my colleagues was using a theodolite. That's the thing that surveyors use in order to measure things out, for property or houses. And we set up the theodolite in the lab, and we established a world coordinate system, and you notice we put down these markers. These are actually sort of printouts of what surveyor marks look like. And what we did was we measured the three-dimensional location in the world with respect to this coordinate system of those points. All right? So what that does is that's going to give us a set of points, x, y, z. And then, of course, given an image like this one, we can find the location of uv in that image. Notice again that I'm using the homogeneous version of the points. Here I'm calling it W, so this is W, U scaled by W, V scaled by W, and that's W. And this was that original equation. So clearly, given enough points in the world in the image, I should be able to calibrate, recover the calibration matrix, and here's how. All right, so first some notation. As before, we've got our world times our M is our projective equation. And notice we've got two versions here. And again, what we're saying here is that UV1 is projectively similar to WU, WV, and W. And in fact, in order to get back UV1, I could take WU divided by W in order to get that. And that's actually what's written on the bottom. All I've shown is that UI, that's for point I have to take the product, that's the first row, divided by what becomes the third row. Same thing for VI. So the point here is that I get a pair of equations for every point. For every point I here, I have an equation that goes from XYZ to UI and XYZ to VI. So what we're going to do is we're going to have to solve for this M matrix using a whole bunch of points. Just continuing, I just slid those equations up, and now I've just carried through, just expanded it through. And one thing you'll notice is that every term has an M in it. And for those of you who know anything about linear algebra, that should start to worry you just a little bit, because typically when I want to solve a linear set of equations, I hope that there's some term that doesn't have a variable in it. And we'll see that in just a sec. So I have this pair of equations for each point. All right, writing it again like that. So now the question is how best to solve this. All right, I'm going to write this a little bit different way. So here I have all my variables, and here for just one point I have my coefficients. So notice my coefficients involve capital X's and Y's and Z's. Those are the values out in the world, along with the V's and the U's, which are the points in the image. Now stretch way back into your memory from linear algebra, and you might remember that usually you were solving equations of AX equals B, and you could have more equations than unknowns, and you'd solve to a least squares solution. But there was a particular kind of set of equations where the right-hand side was referred to as a homogeneous set of equations when they were all equal to 0. And that's why this is a homogeneous set of equations, not just homogeneous coordinates. These things are all sort of related, and when you get really, really old, you'll figure that out. But for now, you can just remember that these are homogeneous equations. So the question is, how do we solve that? Because obviously there's a trivial solution. What's the trivial solution? Well, if a times x equals 0,